scratch.
Thanks. So, hello.
Hi.
So today I want to talk about parallel and thread safe Ruby at high speed with truffle Ruby. My name is Benoit. It's French. I come originally from Belgium, and I moved to Zurich here beginning of December. So it's quite recent. So I'm curious to meet you guys and see what we do in Ruby around Zurich. First I have to show you this, which means what I talk about is a research project, and so you should not buy Oracle stock based on that. So I now work at Oracle Labs, and we are developing a Ruby implementation, which is called Truffle Ruby. Do I speak loud enough? Is that okay?
Yeah.
And I've been doing research as a PhD for 4 years in Austria, actually. I'm doing research on concurrency in Ruby. I wanted to improve on that because obviously Ruby was not very good at concurrency. I've been working on Truffle Ruby since it was created, almost. So now for more than 4 years. I'm also the maintainer of Ruby spec, which is the set of specs for the Ruby language itself. And I'm also MRI committer. So today I want to talk about two things. First, I want to introduce what is Truffle Ruby, and also talk about performance, because it's the most exciting aspect of it, probably. And then I want to talk also about my research as a second part. So first line you already know. So Truffle Ruby intends to be high performance, to really reach a new level of performance that other Ruby implementations just never reached so far. Try to be as fast as it is for fastest just-in-time compiler for dynamic language. For instance, V8 for JavaScript. We try to be as fast as that for Ruby. We use the Graal just-in-time compiler, which is what helps achieve this. And we target full compatibility with CRuby. There are like very few exceptions. We always try to be as compatible as possible. And this means we also run C extension. Because a lot of Rails app out there and Ruby application use the extension, and there's just no easy replacement. So we want to run that, and we actually support quite a bit of that. It's all on GitHub, it's open source, you can check it later if you want to. There are actually two ways to run Truffle Ruby. One way is to run it on the JVM, on the Java virtual machine. And the main advantage here is you can interoperate with other JVM language, including Java. And this provides great performance. Now, the default mode what we run in is what we call Substrate VM. And Substrate VM is basically a ahead-of-time compiler that compiles Truffle Ruby, so our Ruby implementation, and Graal, the just-in-time compiler, to a native executable. So I won't get too much into details there. But the main idea is like this whole thing is initially Java code, so Truffle Ruby is written in Java. Graal, the just-in-time compiler, is also written in Java. And we compile all of this to a native executable. And the advantage of this is we have much faster startup, because for instance, like the JVM doesn't start in 1 second with anything significant, but here we actually can start in 25 milliseconds. And also it's faster warm-up, so the time it takes until your Ruby application is fast is also better, because here the just-in-time compiler is pre-compiled itself, so it's already optimized to compile your code. It's a bit of a meta thing, but yeah. It's also lower footprint, because you don't have to do that class loading or loading part of the Java code and so on. All of this is done ahead of time. Then basically the only memory we need is what the Ruby interpreter needs and nothing else. And the JIT, of course. And the performance is still great in that configuration, so that's why this is the default, basically. And the main advantage of the JVM is then if you want to interoperate with other JVM stuff. Let's use something else. So I guess you all heard of the Ruby 3x3 project. And the goal of this is CRuby or MRI 3.0 should be 3 times faster than CRuby 2.0. And I intend to do this with a just-in-time compiler, which is called mjit. So that's interesting, it's a good direction. I think that Ruby finally gets a bit faster. But my question is, can Ruby be faster than 3 times CRuby 2.0? And to illustrate this, I want to make a demonstration. And I will run what is called OPT Carrot. So OPT Carrot is the main CPU benchmark for Ruby 3x3. And it's actually an emulator for the Nintendo Entertainment System. So let's have a look. This is too small. Okay, can you read this? So the baseline for Ruby 3.3 is Ruby 2.0, so let's use that. And so here we just run the benchmark. So you can see here we have our emulator and we have this game called Landmaster, which is used for the benchmark, and we can actually play it. But we see it's not really fast. So when I move around, you can see there's a bit of lag. And the aim of this game is very simple: it's connect all the computers together. Now you see, like here it lags a lot. So the original frame per second of the NES is normally 60 frames per second, but here it's only 34, so that's not fast enough. So we can use the latest Ruby, latest C Ruby, which is 2.6, and I can run it. And there it's 43 frames per second. So well, 10 frames per second better, but still not 60. But now we can also use mjit. And to do this, we do the --jit flag in 2.6. And now it gets actually a bit faster, around 70 frames per second, which is nice. But now we can also run it on Truffle Ruby. And there it gets more interesting. So there's two modes I explained earlier, with JVM or SVM, like Substrate VM. And here it's a bit better on JVM. But Substrate VM is very similar in the end. So what we see, it starts horribly slow, right? It's like 10 frames per second. But it gets faster, because the JIT now learns what we're executing. It optimizes it compared to machine code. And optimizes much better than traditional JIT. So it's a bit unstable until it really learns the program, but then now we get into 250 frames per second, right? Which is like, yeah, it's way ahead of the competition, let's say. So you can also play it in this mode. The problem is the time is frame-based, so it means I have much less time than on 2.0. And yeah, now again, like we surprise at it now. It's like we're doing something completely different, so we need to re-optimize things. But soon enough, it knows about it. You can see I've been doing a lot of hard research playing this. And it gets more complicated. That seems wrong. And now the time is like, yeah, kidding. So I used to play this on my older laptop, which was a bit slower and it was manageable. No, it's not wrong. That's okay, I think you got the idea. So here we can see the frame per second, right? So you can see like interval we reach over 200, which is like 3 times faster than mjit. So he did 3 times, maybe 3 times 3 or something like this. And so what we saw is here, like if you want to graph it, like initially Truffle Ruby is this green line and it's pretty slow in the beginning, but once it learns the program, when it optimizes, it sees how you use the methods, or you use, for instance, addition, you use it only on integers or something else, like you have also big num in it. Once it learns this, it's very fast. And like this level of difference here is like, it's a big margin, right? And today I want to try to give you some insight into why we do so much better on performance. And this is not only on a PT carrot, but for instance also on classic numeric benchmarks. We also perform very well, like typically between 10 and 15 times faster than MRI. And you see Ruby here, which also has a JIT, but performs a bit better, but not the same level. And then if you run mjit also has its own set of micro benchmark, and actually they run it against Truffle Ruby at some point. And here's the native configuration, so it's the default one. And you see there we're actually 30 times faster than C Ruby 2.0, and mjit itself is 4 times faster. So means like really like we are good at optimizing all this kind of benchmark, and there's just like a different level of how much we can optimize that code. Other areas is like, for instance, rendering, template rendering is something we are pretty good at. For instance, on a simple ERB benchmark, we are about 10 times faster than MRI. And this is due to a different representation for strings. So for instance, string concatenation in MRI is pretty slow because it involves copying and reallocating. While if you use something else like ropes, which is used like in text editors, then it's actually constant time.
What does it use?
So what we do is, we implement concatenation differently. So when I concatenate two string, actually, instead of like copying this one, making a bigger buffer and copy the stuff, we're like, okay, with these two one, and we have a new nodes here that represent the virtual concatenation of them. And we only actually like flatten it when you write it to the network or something. There's a talk about this if you want more info. There's a lot more stuff we do very well as well, but we don't have infinite time either. The big question is, do we run Rails? And the answer is yes, to some extent. So I think the Rails new almost works out of the box. There's like maybe 1-2 small workarounds. We also have a small blog application. And we're trying to run Discourse because Discourse is used as one of the benchmarks also for Ruby 3x3. And actually I have a fair bit of it working already, but currently with a few patches, so we need to fix a few things like there, and we want to like do it properly, like fix everything in the interpreter so it just works without changing anything in the application. But the big challenge of running big Rails app is they often have tons of dependencies, over 100 gems, for instance, and like one that doesn't load is enough to not be able to run it, right? And then you have to start to work around it, and that's not ideal. And many of these streams are also C extension, which tends to be more complicated. So recently we got actually a new approach for C extension that works a lot better. Like before we actually had to, like, for instance, for the PG driver or MySQL2, we actually had to patch quite a lot of places and so on. And this doesn't scale. If we have to patch every C extension to make it work with us, it's never going to work. So now we have something completely different where we kind of simulate the GC for MRI for C extension. And the end result is this basically like many C extensions no work out of the box. You can just gem install it and that's it. And so we support, this one is I know we support all of these, but I guess many more now. Maybe I can show you a small Rails up. Click with it. That's it. Is that? Okay. Yes, it's a very simple block, nothing very fancy. But it works, and it was just created with like Rails new, some scaffolding, and that's about it. Mm-hmm. That's I think Rails 5. So, how is true for Ruby so fast, basically? And I made two concepts, which is the partial evaluation, which is kind of new. I think it's something that was introduced by our project and never really used in practice before, at least for JIT compiler. And then we use, of course, the grad JIT compiler, which has a number of optimization, as we will see, that helps a lot as well. Implementation-wise, like integer plus, for instance, basic primitives, they are written in Java, because Software Ruby itself is written in Java, but the core library is written in Ruby itself. So this is like Rubiness. So actually you have a lot of the core library is defined in Ruby itself, and then just what we need that we cannot express in Ruby code, like addition, then of course we need to use Java. So let's see how a Ruby interpreter can execute your program, right? So we have a very simple function method foo, and what it does is it maps an array of two numbers and triple them. Very simple. And the first thing any Ruby implementation will do is pass this text into an abstract syntax tree. And actually, it's three abstract syntax tree, because there's one for the method here, and the method it only calls map, and it calls that on an array literal, and then the only argument is the block. Then the block itself here is also a different AST, that then multiply the argument by 3. And then finally, map is also in the end an AST. If it, for instance, if it's implemented in Ruby, it's its own logic. And then what it will do is obviously read from the array, build a new array, and call the block for each element. Now, what we do in truffle Ruby is very similar to this. Instead of just an abstract syntax tree, we do what we call a truffle abstract syntax tree. And it looks very similar, but the main thing is here, actually, each of these nodes is now a Java object. And each of these nodes has an execute method, which defines how to execute this node, how to express the semantics. So for instance, here we have a multiplication node, and what it does is execute the left child, execute the right child, multiply it, return that. But that's a very simple way to implement an interpreter. And normally this way is actually very slow, and like Ruby 1.8 was a bit like this. It wasn't very fast. But because we have this trick of partial evaluation, we can actually make it very fast. And the idea is, so this magic process, which I will explain later, of partial evaluation, it takes this truffle AST, and then we get out of it is a compiler graph representing how to execute the Ruby method. And this is basically just an intermediate step, because once the JIT takes this, it then emits machine code out of that. So basically, we will be able to like emit machine code for this piece of the truffle AST. Now it works is we start from the initial node, the top node, so like this one, for instance, and then we see, okay, what's the execute method is doing, and it's like, oh, the execute method is actually just using this one, and then this one is executing this one and this one. And actually, we go through every node like this. We inline the entire AST, and then we get like basically a lot of Java code, and then we can optimize that. So let's see in action. So we have our foo method again. And the execute method of this foo is just like a method, just execute what's inside the body. So just execute the child node. And the child node here is a call node, is a call to map, right? And the call node would have some logic how to call a Ruby method. But first, before calling anything, it has to execute the receiver and the arguments. And executing the receiver means the receiver here is an array literal. And this just creates a new Ruby array with the value executed. And the values are 1 and 2, so they are integer literal, and they just return that 1 and 2. And the interesting thing is while we do this process, we also do some kind of constant folding. So we know we are compiling foo and not any other method, we're just compiling foo. So when we read this link, like here, this child is actually a field, right? Normally we would have to read this field in normal Java code, but here we don't, because we know this AST is constant. And so because it's constant, we can fold everything, and so all these execute methods here are all together like this. And so the equivalent thing we get after partial evaluation is this. So we have like the equivalent of a foo Java method, and everything is in line. We know we already call map, we know which block, we know which array, which value, and everything. Now this is done for foo, but we also do it for the other AST. So we also do it for the map AST, and we also do it for the block AST. Again, we do the same process. So map here just iterates the array, call the block for every element, and block we just multiply by 3. And then another thing that happens also is we do inlining at this point. So what we see is like when this foo method call map, we actually remember which AST we call, which method we call. And we see, oh, actually we always call map, right? It's not very surprising. That's what the code tends to do. So we always call the same thing. And then here when we call the block, we see, oh, actually we always call the same block. So when we see this, like maybe this was inlining. Like maybe putting all this AST together into one, which is very easy. You just rearrange it and done. And then now we have a lot more code we can optimize together. And we can start to like optimize things that are between different methods and blocks. So once we inline everything, we have something like this. So we have the original array with 1 and 2, and then we create a new array of the same size, and then for every element we'll call the block, but this is inline, so we just multiply by 3 directly. Now at this point, the gradual system compiler kicks in. And here we start to have some optimization classes. The first thing it will do here in this case is to do what is called some escape analysis. So it will see like this array here we create, we allocate a new array, but actually it never escapes the method. It's like the return value, it returns a new array, but it doesn't care about the original array. And actually you read some stuff from the array, like you read the size of the array, and we read elements from it. But the instance itself, the Ruby array instance itself, doesn't escape. So we don't need to allocate it. The compiler can figure this out, and we just replace every usage with what is actually like what's in the fields. So what happened is this. So the array becomes just the storage, which is this int array internally. The size of the array here was 2, because it's like, okay, the size of this is 2, so this is it. And reading from the array is just reading from the storage in this case. The next thing is now we are reading here from an int array. So what we read must be an int, so this is always true. So there is no point to have another branch that do more complicated semantics. Now the compiler says, oh, there is a nice little loop here. It always does exactly 2 iterations. And inside the loop, there is not so much code. So maybe it's worth duplicating this code for every iteration, because there are only 2 of them. And then the code will be much simpler and easier to optimize. And it does this. Now it sees like, okay, actually, like we're reading from array storage 0, and array storage is just there, so it can, in the compiler graph, everything is linked together, so it can see like, this is what creates it, this is what uses it, so it can just forward the value, and array storage 0 will just become 1 and 2. And actually, the array storage, we don't need it anymore after, so it's gone. Then finally, here it sees like this multiply exact, it's like multiply but also consider overflow. But obviously 1 times 3 doesn't overflow, so we can just do it. And we rearrange the code and we got this, and this is basically the most optimized code you could get for what we got initially. So we transform this into this Java code, which basically if we transform back into Ruby code, it's like, yeah, okay, it's the answer. It's what we could reason ourselves about. And this looks simple, but actually you saw behind the scene it's not that easy. And actually only Truffle Ruby managed to have this level of understanding of Ruby semantics. Then you can, yeah, of course this is then assembly, and then assembly just does, you can imagine, write 3 to memory, 6 to memory, the return a new array, and that's it. So that was Truffle Ruby. And now to compare a bit, I want to compare with mjit, so the method JIT in CRuby. And then the first step is also to pass the Ruby code to an AST. Then it's transformed not to a truffle AST, but to a bytecode, which is just another representation. It doesn't really matter here. But the point is that when a method is called many times, mjit will generate C code. So it actually like printf C code, and then pass it to a C compiler, which then generates a share library, which you then load back. So it actually generates C code. That's the way they choose to communicate with the compiler, because of course to communicate with a C compiler, that's the most convenient. And so when they have this Ruby function, it's more or less translated to this, which basically like looks like C extension code, basically, right? So it's like, okay, the values are here, and then there's RB something, and then function call with a block with this map. And then they can also like compile the block separately. So here the block could be like just multiplied by 3, but it's inline and specialized for like fixed num and float, for instance. And then at this point, GCC or client kicks in, and what it optimizes, not much actually. The only thing it can figure out is like this float is true a float. No, it's not a floating point, it's an integer. So you can say, okay, that branch doesn't exist, I remove this, and then I just keep this one. But that's it. It cannot go further because it doesn't know how to go in this or this or this, because this is already compiled to native. It has no idea what it does. It has no idea what the logic does. And so this is like currently the main limitation of mjit is it doesn't know anything about the map function, for instance, because that's part of the Ruby binary, but it doesn't exist in source form at runtime, and it doesn't know like how to understand, how to go through it, how to like inline it, how to optimize it. So in summary, like we can say the performance of Ruby can be significantly improved. Like it can be up to 10 times faster, for instance, on a number of benchmarks. And Truffle Ruby is an example of that. So I think the message here is like there's no need to rewrite application in another language than Ruby for speed. Like Ruby can be as fast as JavaScript, another dynamic language at least, which is already pretty good. And that's like within a factor of 2 of Java, which is probably good enough for most companies. One crucial point is the JIT compiler needs access to the code library, like to this map function, for instance. Otherwise, it's very limited, but it can only understand user code that never use core library method, but Ruby code use core library methods everywhere. So if it doesn't understand them, it cannot do much. And it also has to understand a Ruby construct. So here's for MJIT, for instance, a bit more complicated because, for instance, in C, there is no concept of an object allocation. There's no object. Because in MRI, an object allocation is just like bump a pointer and write to memory. But the C compiler doesn't know that, oh, maybe nobody will read from this from another thread or something. It just cannot assume that. So there's some challenges for MJIT there to address. Basically, like be able to communicate better with this compiler. Like in our case, we can do this better because we're in Java, so there's already the concept of object allocation. But also we control the just-in-time compiler. And so we can give it more information if needed. Okay, that was the first part. So now I want to talk about what I did during my PhD. Which is I want to make Ruby another dynamic language parallel. And the problem I noticed and the problem I wanted to work on is like dynamic language, not just Ruby, have poor support for parallelism. Because again, none of them has really a good solution for it. And often it's not actually due to the language themselves, it's actually due to the implementation. And so there are actually three types of implementation. The first type is the one with a global lock, and in this we have like CRuby or CPython, and JS could also be JavaScript could also be considered there to some extent. And then there's a global lock, so there is no parallel execution of Ruby or dynamic language code ever in a single process. So the only possibility there to achieve parallelism is to use multiple processes, and that wastes memory, duplicate resources, and there's slow communication between these processes. That's like kind of like the last layer to do parallelism in CS, use multiple processes. Then the second category, which is more interesting, is what I call unsafe, where Ruby and Rubiness are. So they actually allow Ruby threads to run in parallel, but they give up on important guarantees. So for instance, if you call array append concurrently on the same array, you might get an exception. That's a problem now, because in the documentation, array append appends one element to the array, and not like, oh, might throw an exception. And then we have a third category, which is like, oh, let's avoid the problem altogether and ignore these shared memory problems, which has its use for sure. So this is like share nothing or share little. And in that we have JavaScript, because it has kind of an actor-like model with the worker thing. Erlang is in that too, and the guilds, which is for Ruby 3, I will expand on that, is also in this model. There the problem is you cannot pass object between threads. It's just impossible. Just like either you need to deep copy or you transfer ownership, but then you cannot use it anymore in the original thread. So there's something in it, like when you use it that way, it's much more restrictive. So yeah, let's expand a bit on guilds. So that's a new concurrency model for Ruby 3. The advantage of this is there's a stronger memory model. So the semantics are simpler. There are no low-level races because there's no shared memory. Point. Actually, there is shared memory at the process level, but it's like in your Ruby process, every guild would have a different heap, different Ruby heap, and there's nothing in common in those heaps. So the big problem there is like you cannot share pass or object or collection around, and well, this is an object-oriented languages, so it feels a bit weird. So either you deep copy them, but if the object is large, it takes a very long time to deep copy it. Or you transfer ownership, but actually there's a catch. When you transfer ownership, you actually need to deep copy everything except the last layer for implementation reasons, so it's not much faster. And so this is a problem. Like compared to a sequential program, when you parallelize with this, then you have this copy overhead. And of course, you always have to balance it. Like if the copy overhead is too high, then maybe the parallel version is slower than the sequential version. That's very bad. And it also means like shared mutable state can only be accessed sequentially. Like it has to be in its own actor, its own guild, and every time it has to be communicated from the outside. But it's one at a time. So it's something like a concurrent hash map, where normally you can read from multiple threads at the same time. Not possible in the actor model. Or you need like very special data structure that kind of break the model for that. But the normal way, like your own business logic, no. not parallel point. It's a different programming model. So for instance, if you have code using Ruby threads, then it won't work with Girl just like that. So we need to adapt it because you can't pass object around. But in the end, I think it's a complementary solution. Like there are some programs which are like very nice to express with this like share nothing and share little programming model. Like for instance, I don't know, like some IRC chatbot or so on, like something that tends to be very isolated, and like you can put the rows and you don't need to like share a lot of state together. Then it's quite nice. But some of them, like for instance, ray tracing, where like you would say, okay, I want to render this picture, and I will give this part to a thread, another part to a thread, another part to a thread, another part to a thread. That's like much easier to do with shared memory, because you don't have to just copy the screen all the time. You can just write to it, and everyone writes to a different part. So I was saying, like, Ruby and Rubinius are unsafe, and I want to show an example. So I create an array here, and I create 100 threads, and each of these threads is going to append 1,000 integer to the array. Then I will wait for all the threads, and I will print the size of the array. So at the end of the program, I should get 100 times 1,000, 100,000. And sure enough, if I run this on Ruby, I get the right answer. Of course, nothing runs in parallel, so this thread is just like, yeah, waiting for each other, but the answer is correct. I can run this on Ruby, I get two possible results. Either I get a random number, or I get an internal exception. And if I run this on Rubinius, same thing. Either I get a random number, then show it, or a different exception. And that's kind of bad. Like, it's like if you have something in production using parallelism, maybe locally there's not enough request for it to happen, but then in production maybe the request will just die with this. It's not very nice. The reason why we have this smaller number here, it means some of the appends were lost. So the race was done in a way that basically they both incremented the size at the same time, but not atomically. So it was like 3 and 3, 3 plus 1, 4, write 4, write 4. It's like, oops, one incremented 1, but added 2 elements, right? So this is very bad too. It means basically data corruption. So a workaround for this implementation, and yeah, the only way the relay recommend to address this is like, okay, you need to do some synchronization. So either you can use a new text like this, or you can use like a concurrent array.mu, which is from the concurrent Ruby library. The main problem with this is it's very easy to forget to use that, and then again, like if it only happens in production, hard to reproduce and so on. So I don't think we want unsafe semantics by default. Also, the synchronization is not necessary. Typically, these two add significant overhead. And they actually currently only allow sequential access to the array, which is sad because like, if you access an array, different part of the array, you should be able to do that in parallel, but actually not. I think the biggest point is like this, like array and hash are thread safe on Ruby, and if they are not on the implementation, then just incompatible point. Instead of example in Bundler and RubyGen, so like, yeah, they don't work on Ruby and Rubinius because array and hash are not thread safe. But of course, they don't do this by intent. I mean, like the reason they do this because to make them thread safe, array and hash, it would be very expensive and it would affect sequential performance, which they don't want. So big research question here is like, how can we make collection thread safe and not have an overhead on single threaded performance? And one more thing is I also want parallel access. I want to access my array in parallel and I want to access my hash in parallel, especially if I access different parts. There's no reason I can't do that at the same time. I think the problem is even larger than that. It's not just collection, because objects are kind of collection in dynamic languages. Because an object you can add or remove instance variable, typically is the same power as a hash table, even though they're not used with the same pattern, but we have similar problem. And so because you can add or remove fields, and we can add 100 or 1,000 fields if we wanted to, we need to grow the storage for this object dynamically. Like we need to expand the storage to store more instance variables. And due to that, we have the problem that concurrent writes and extending the storage, we might lose some writes. So here's an example. So I create an object, and then I create a thread that will set the field A to 1 and then update it to 2. And the second thread will set the field B to string B. I wait for both threads, and one possible outcome is that actually I get 1 when reading A. So it means like this one was completely lost. And this is actually possible on Rubinius. And the reason is like, okay, initially thread 1 sets set A to 1, very good, we store it. But then before it sets it to 2, the second thread starts, and then it says like, oh wait, the storage only has a capacity for 1 instant variable. So I need to grow it. So to grow it, I have to make allocate a bigger chunk and copy the existing part. And it does this, and then it will set the new value in it, and then assign the storage to the new storage. Problem is, first thread wrote the update on the old storage, which is now lost and unused. And so this update is lost. So this is something that should be fixed, but that's some cost we'll see. And the main idea is like, oh, what can we address like this? Like, how can we avoid overhead for sequential program and still have thread safe collection and objects? Is to distinguish, to only synchronize on what we need. So my approximation here is like only synchronize on object or collections that are reachable by multiple threads. If an object or a collection is reachable by only one thread, there is no need to synchronize, there is no concurrency. So here is an example. So I have thread 1 and then a few objects here, and thread 2 and another few objects. All objects are like white currently and unsynchronized, right? Because they can only be accessed by one thread. Now what happens if the queue is put in a global variable, for instance, then it's accessible by every thread. Or if we give the queue somehow to thread 2. Then at that point the queue becomes shared and becomes synchronized. There's some synchronization accessing it. But not only the queue, but everything reachable from it. Because of course thread 2 now can put a message out of the queue and access everything of this and mutate it. So we need synchronization at that point. And to do this, actually quite simple. We don't need much. Of course, we need to track it at runtime, right? And so when this happens, we need to track it. And the way we do this is a write barrier. So it means like when you write to a shared object or to a shared collection, whatever we put in it is going to be shared as well because it becomes reachable through it. So write to a shared object field, then we share whatever is in it. So the hash, the key, and the value. And in an array, then we share the element. In the hash case, the key and the value. And with this approach, actually, you get pretty good result. So this is single-threaded benchmark. And this is a benchmark that basically use objects. And we see like unsafe is Truffle-Ruby initially, and safe is Truffle-Ruby with thread-safe object, with this local and shared distinction. And there is basically no difference, right? Red and green are the same everywhere. On the other hand, if you would synchronize on every write, which is like, for instance, what Jeremy do, then on some benchmark can be pretty bad, like up to here 2.5 times slower on Embody. Because then every object write becomes more expensive. But here, since it's single-threaded benchmark, all objects are local, they can only be reached by one thread, so we have no overhead, we have no synchronization. And we can do the same trick for collection, of course. So again, Truffle-Ruby, the unsafe version, and then the one with the thread-safe collection, same performance everywhere for single-threaded benchmark. So now let me detail a bit more like how we deal with, for instance, arrays, because that's quite interesting. So the first thing I need to introduce is array strategy, array storage strategies. This is an implementation technique that's used in most virtual, state-of-the-art virtual machines. And the idea is we represent the array with different kind of backend, with different representation behind the scene to fit most exactly what's in it. So initially, for instance, when we have an empty array, then it uses this empty strategy. So there's no storage at all. It could be like null or nil or whatever. Then when we append an integer into it, then it becomes an int array. Here it migrates like this. Then if we append later an object array, an object then becomes an object array. So the most general one is this object array. But the reason we don't use it all the time is there's an extra cost due to it. And because of this object array, means we would box primitives like int, long, or double. And also it's an observation that even though it's dynamically typed languages, so we can mix types in an array, in practice very few cases do. So in practice, almost all array are like, if there's an integer in it, probably all the other elements are going to be integer. It's rarely a mix. And so here the advantage is then, of course, if we represent an array just as an int array, then means it takes 4 bytes per element. It's very compact, it's very efficient. I can access it directly. I just read the raw memory and that's it. Well, in like in MRI, for instance, each element would take 8 bytes, and I have to unencode it from the type pointer and whatnot, and it will be less efficient. So we have this array storage strategy, and that already exists. And what we do is, okay, wait, first the goals. So I want to add this shared array. I want to make this to work also and make it thread safe, right? And this is complicated because now the array it can move between this and change the storage and so on. Like if two threads try to change the storage at the same time, bad things will happen. So how do we fix this? And I want to make all array operation thread safe, so just basically the same semantics as MRI. I want to preserve this optimization of storage strategies. And I want to still enable parallel reads and write to different parts of the array. And the way I did this is like, oh, well, let's add another dimension to these array strategies, which I call concurrent strategies here. And actually 2 of them. That's what I call shared fixed storage and shared dynamic storage. The shared fixed storage is like a strategy that's specialized for some usage pattern of the array. Basically, it assumes like, okay, this is an array that's basically like kind of a fixed size array, like an array in Java. Like you're gonna access it by just reading it, but you're not gonna append or delete element in it. And by having this more like specialized thing, then we can actually access faster. We have like no overhead in that case over the classical things up. But now what if we actually append an element or delete an element from one of these? Then we need to go in the general case, which is here the shared dynamic storage. And there, because there are like hundreds of methods on array, and they do all kind of crazy things, we need to use a lock to synchronize. There's no way to have like a lock-free implementation of something very fast. It's just like we have to use a lock point. And what we see, for instance, here we have some benchmark. We just do like read from an array or read and do some writes. And we have a lot of different things here with the thing. But we do this from one thread to 44 threads. So this is on a big machine with actually 44 cores. And what we see is the local, so when the array is not shared between threads, the performance is pretty good. It's like here we reach like 30 billion array accesses per second, which is quite good. But then if we use shared fixed storage, which was this guy, we have the same thing, the same performance. So that's why this one exists. So like if you actually access the data like this without like concurrently modifying it in like pretty big ways, then it actually optimizes nicely. But then as soon as you start to use a lock, so all the other one are actually using some kind of locking mechanism, and performance like bam, 3 times slower at least. And so there we have tried different kind of locks. So we have like the reentrant lock is like a global lock basically. It's an exclusive lock. So there doesn't scale 44 threads, not any faster on one thread. Then you have something like stamp lock, which is like a read-write lock, which scales for read, very okay. The dark green here, but doesn't scale for write at all. So that's not good enough. So we need to invent something new, and that's what we say. There's something called the layout lock, and this is just a variant. The library layout lock is just a variant of it. But basically has 3 modes of access. You have read access, write access, and layout change. So layout change means, okay, we change everything, like we change the strategy, or like we need to delete an element in the middle, then we really need exclusive access to the array. But the read and write can be in parallel. And so under these two, actually scale for reads and for writes. I can run this on bigger benchmarks. This is actually the NASA parallel benchmark. It's a suite of rather old benchmarks that were originally written in Fortran. That's typical scientific computing. And they were translated to Java and then to Ruby. And what you see here is the scalability. So how much time we are faster on n threads than one thread. And you see actually like the scalability curves are basically very similar for Java Fortran, unsafe for Ruby, and thread safe collection. They're all the same, so you can say basically like, oh, we scale as good as Java and Fortran, which is pretty good for this kind of work. The reason here is simple, because it's like very regular workload. We use mostly like this shared fixed storage strategy, so it just works nicely. So about the end. So I showed that the performance of Ruby can be much better, and for Ruby is an example. We can have parallelism and thread safety, and like based on the simple idea of like whether an object or collection is reachable by multiple threads, then we synchronize, otherwise we don't. Then we can actually go pretty far, and we can have parallel array and thread safe, array and hash. And so in the end, yes, with this, we should be able to run Ruby code in parallel, have the most important thread safety guarantees, like we have with the global lock, but still, yeah, scale to many cores. If you want to try to for Ruby, I integrated it with all the Ruby manager I could find. So you can try Ruby install, RVM or RVM, and it should just work. If it doesn't, please report a bug to us. And then yes, Ruby is part of a bigger project, which is called GraalVM, and was released last year actually, publicly. And it doesn't only contain Ruby, but also has a JavaScript runtime, a Node.js runtime, R, Python, and a VM bitcode runtime, which means we can execute C, C++, and more stuff, all in a single VM. The advantage of this is all these languages can interoperate, they can call each other easily and efficiently. It means, like, for instance, if you call, I don't know, Python from Ruby, you can actually inline through it, and the JIT can see through both languages and optimize them together. So basically, you can call, I don't know, Ruby to R to Python to C, and it will be just as fast if you wrote the whole thing in C, which is kind of cool. Yeah, this LLVM bitcode thing is also what we use actually for C extension. So we don't actually, when we have a C extension, we actually interpret it. We have our own interpreter for C code, which has a JIT then, and it's the same JIT. So we interpret C, we compile, just then compile C and Ruby code together. So if you have some code going Ruby in C and back, then you can just inline through everything, and it's much more efficient. And finally, this comes in 2 editions. So there's an open source community edition, free to use. The release is on GitHub. There's an enterprise edition, if like for bigger companies that want some support, and also like basically to support the research group behind this. And that's it. Thank you for listening. If you have any questions.
What's the support so far, maybe on Heroku?
Nothing yet. But I guess we'll get there at some point. The Heroku is an interesting business model where like they give you basically no memory. Like 500 megabytes is very small, even for MRI, right? So I'm not sure it would work there. Would definitely not want to run a JVM there, but we could run with Substrate VM probably some workload. I think it could be interesting. So the answer is we didn't try yet, and there's no integration yet. But I think it will happen in the future.
Or alternatives?
So I'm pretty sure like at some point, hopefully like on the like Oracle Cloud or other clouds, Truffle Ruby will be available and integrated, so you could just try it and run your application and see how it goes.
What is still missing?
Sorry?
What is still missing other than running Rails?
Not much, I guess. So running Rails and like lots of C extension is basically the next goal. And then of course you want to have number on how much faster we are on Rails. That would be a big thing. Like, you can say like, oh, we're 2 times faster on Rails. That's already something.
Mm-hmm.
And I guess like some companies would get interested.
Yeah.
That's pretty cool.
Is any of your ideas flowing into the Java team? Because I think they could also profit from this.
Right. So, well, one part of this GraalVM project is the Graal JIT compiler, which is written in Java, and that's actually getting more and more integrated. So now, as of the recent release of Java, Graal is actually part of it, and you can use it. I think still behind the flag, but eventually this JIT compiler will replace the old JIT compiler, probably at least. They probably replace the old JIT compilers that were there in the JVM. Because basically a simple thing is like, it's Java code, so it's more maintainable. And the old thing was C++, and nobody wanted to touch it because it's so complicated. So there are some gains too for Java, like where we already run this code faster, and Scala, for instance. Scala code also typically runs faster with Graal. Substrate VM, which I introduced in the beginning, can actually take a Java application and compile it down to a native executable. So just like GCC would for C code, basically doing the same kind of thing. That's very interesting for, like, I don't know, function or serverless computing, where like you could ship your Java application as a simple small binary. It doesn't consume much memory, that starts instantly. And that can be a big thing. So some of the stuff is flowing back into Java, yes. We're trying to build like a bigger ecosystem with a lot of language. Like behind all this is like a common framework which is called Truffle, and we're building on that, trying to make it easier for people to actually build a language implementation and have it fast, and still like keep it not too complex.
Sorry, go on. Go.
In my company, we have a team that works with R and a team that works with Ruby. So it would be possible to run both, like let's say a Ruby application and some R script together, and
Yeah,
they could share data.
Yes, absolutely. So there's actually someone external working on this, Rodrigo Botafogo, I'm not sure his last name, but actually like made a blog post about this, like where like it did some plotting with ggplot in R and called that from Ruby. So there's some integration. They can have a nicer layer to like interoperate, but even like out of normal GraalVM, you can already do this. Okay. So you can really like have a function in R, you can call it and pass it a Ruby object and so on.
Okay.
But that's something that doesn't exist before, right? Or if there is, it was only like a 2 language mapping maximum. Here we have like n language mapping, right? So it's something that we are very interested in, but people are like didn't dare so far too much to try because I don't know, it's something new.
Do you have any publications about this? Because I think this array or this collection idea is very abstract. It's extremely interesting because you can really do a lot of things with any language, not only with Ruby.
Yeah, of course. So yeah, actually I got a paper about this as part of my PhD. So I actually have a lot of publication as well on all of the kind of ideas in the project like this. So storage strategy is actually not so new. It was introduced in, well, kind of, it was introduced in PyPy a bit after 2000, I think. And so here I did a more like general version with concurrency in it. There are other stuff like the object model. It's actually introduced by the Self guys in 1989 or something. That's older. There's also a version like where like, okay, I make this thread safe. Right? So yes. If you want links about that, yeah, just go on the graalvm.org website. I think we have a list of publications.
So you contribute to CRuby, right? So what's their guys' opinion on Truffle Ruby?
I don't know. It's a lot of individual opinion, I guess.
So they open to maybe basically throwing away the bytecode generation approach and using something like partial evaluation as well?
I don't know, because the project context is very different. Like for us, you have to imagine GraalVM is currently a team of 50 people working on it. It's like 4 people on Ruby, so it's a lot of different sub-projects. But CRuby is like basically 4 or 5 people full-time, and that's it. And all the rest is open source volunteers. So they have not so many resources, and that's why they did this mJIT approach where they emit C code, because they don't have to write their own JIT, which like takes years, like Graal took, I don't know, more than 5 years to be written, and there was already a lot of background from the Java compiler. But writing a JIT from Ruby from scratch would take kind of forever, probably. So you need to be like one of these huge company and spend a few years on it. Like, yeah. So I guess for them, like, it's mostly a choice of like for mJIT, like based on their resource and how can they maintain this and make it more incremental. Like here was something like where, okay, we don't reuse so much of the MRI interpreter. We can reuse the C extension, but not the core or anything, because we want to be able to optimize through it. And C code is just not a very good medium for that. So I don't know, sometimes they are impressed, like, I don't know, I posted on an issue about some guy working on mathematical libraries and on a benchmark, and they were like, oh, cool. But yeah, I guess the main thing for us is like, we'd like, of course, to get more adopted, more users, and you can see our stuff is used. I think like Ruby is one of the prime examples here because we already have a huge speed up over the standard implementation. But for instance, JavaScript, well, they're the same level as V8, but they're not much faster. Different kind of advantages. Yeah.
When did you, well, not you personally, when did the project start?
So about 4 years ago.
Okay.
So Chris Seaton started it as an internship, and then the project was taken on and developed since then. So yeah, you can see like it's been 4 years. We have about 4 people working on it during these 4 years, and we're still not done yet with compatibility. So.
What would be the first gem I will get stuck on? Pardon, could you?
Yeah, no Kogari, no, I think it works to some extent. Yeah. So for a long time, database driver were a problem. The main thing there was like our approach to C extension. We said like, oh, we're in a managed VM and we interpret C, so everything can be managed. But no, this is a dream. It works for C extension that are written for performance, because then, okay, it's just like a different way to write Ruby code. But it doesn't work for C extension and try to bind to a native library, like for instance, database driver or no Kogari.
So PG or...
Yeah, for instance. Because of course then a lot of the Ruby objects don't actually go into native. And then that's where it gets complicated. Because now I have like a managed representation of my Ruby array, and now I have a native representation of it. And the same for the string. Because the C extension API gives you just a char pointer from the Ruby string, and you're like, well, how do I do this? And how do I reclaim the memory? And how do I reflect the updates back? It's all kind of complicated.
And you will go like for low-level operating system access. For example, you run on Linux and you have like libraries that are very powerful inter-process communication and whatever there. And you have C extensions that access that. Does that work, or do you have problem when you are too OS low-level?
So with the previous approach, basically this kind of stuff didn't work very well, because we had to say like explicitly like, oh, okay, this thing is going to native, so we create some kind of indirection from it, and every time we use it, we remove this indirection. But it was inconvenient because you can't do this automatically. Now in the new approach, we just let every Ruby object be converted to native, to some kind of pointer. And then when you use it, we manage to find it back. And then we have to do some kind of GC to find out like, okay, whatever we converted to native, once we are back from it and nothing refers to it anymore, we can release them. So that part, no. In the end, the C extension code, we first compile it with Clang, but not to native code, to bit code. And then, yeah, we execute that with our LVM interpreter, but that one for like very basic low-level stuff, it just called the operating system, so that should just work.
Okay.
There are some stuff that are a bit more difficult, like creating a thread. If you just do a p-thread call directly, it's actually complicated because you need to do some initialization of the Java and the Ruby thread. So there we need to intercept that a bit. Yeah, basic things like, I don't know, open a file and access low-level operating system stuff, we can just let it do in native. There's actually another mode, but currently only enterprise, where this LLVM bitcode interpreter is entirely managed. So that it has to implement the entire syscalls, but then it guarantees memory safety. That means that it's impossible then to access something like out of bound, out of memory to cause a segfault. It's no longer possible to create a segfault. That's something interesting, but something that is very hard to work with for like OpenSSL, which is like a lot of very old C code with assembly and whatnot in it. So yeah. I don't know, that's a bit more new, but that could be interesting also, like, if, for instance, a C extension is not very stable, cause segfault sometimes, then you run it in that, and then you will actually not be able to create a segfault anymore. And you would be able to also, like, see the bug and have a backtrace and say, like, okay, this is what created the problematic access. Yes?
Cool. Really nice. Well done.
So I hope you guys try it, and please report back if you find anything. It would be very helpful.
Thank you, Dan.
Thank you.